Now that we are experts on noise, let's see what happens to the histogram of an image when we add noise to it. For that, we are going to use a very simple example. We see here an image that has only 3 regions and then only 3 values. So if we were to draw the histogram of this image, we will see at different heights, but we actually see only 3 basically delta functions. One that stands for the black region, one that stands for the gray region, and one that stands for this lighter region. And the height of this depends on the area of each one of the regions. So when we add noise with each one of these distributions, how is this histogram going to change? It's going to change from these 3 delta function to something. Let's see what happens. So here we see 3 examples already. In the first example, we took the original image and we added Gaussian noise. This is the type of probability distribution of the noise, and we actually see it reflected here. It's very clearly, there are kind of 3 Gaussian distributions. This is going to be very important. It's going to help us to estimate the noise if we're only given the image, as we're going to see in the next video. Here, we see a shape which is very similar to the shape of the Rayleigh noise. It's kind of tilted and then it goes down, almost like a Gaussian, slightly different. So clearly the shapes here are very different. For example, this is kind of symmetric, this is not. Remember, these are probability distribution functions for the noise, so we are not expecting to see a perfect function. This is all in probability. And here we see the gamma noise. Once again, a shape very similar around each one of the pixel values, a shape that is very similar to the actual probability distribution function. So these are the 3 of them. Let's just continue seeing some additional examples. I'm going to ask you now a question. Which noise do you think we added here to the original image? So this is how basically the image looks after we added noise. Which one of these 6 you think we have added here? Please give me an answer to that. I think it's not very hard to get to the answer if we just compare the shapes. Once again, remember, if we only had the original image, we had kind of 3 delta functions with different heights representing the black, the gray, and the white regions. And now we see very clearly exponential functions. So it was this noise. Okay? We can not see that from the image itself. It's very hard to see, is this Gaussian, is this exponential, is this Rayleigh? You have to really be trained to observe them just from the image, but it's much easier from the histogram. So now that we are really experts, I'm going to ask you again, what's the noise here? Please give me an answer. Just think for a second and give me an answer. Once again, this was the original histogram, and now we actually see kind of uniform distributions, so we see clearly that this is the noise. It's basically around the area of the original histogram, we see flat regions. So this is the type of noise. Now please note that in this image, the same type of noise was added all around the image. Otherwise, for example, if we add Gaussian noise inside this region and uniform noise to everything else, we will see actually a Gaussian here and uniform in the other 2. So we will see combinations of these distributions. Finally, this is the salt and pepper. Salt and pepper actually is not hard in general to recognize from the original image. We see the black dots or the white dots. But I also want to illustrate that in the histogram. The histogram stays with kind of delta functions. But of course, if there was no black, then would be a new delta function at black. Or if there was black, it would be a larger, basically a taller delta function there. And the same for white. So we can see from the histograms what actually happens sometimes. And therefore, we can use the histograms to estimate the type of noise and to estimate the parameters of the noise, as we're going to see in the next video. Thank you.